In this video, we will look at section 4.5 and 4.6, which covers identity matrices, null matrices, transposes, and inverses. So first, the identity matrix. We indicate the identity matrix with a capital I, and it is a square matrix, which means M is equal to N, so it's always 3 by 3, 4 by 4, 5 by 5, 1 by 1, or 2 by 2, etc. And the diagonal entries, so A11, A22, A33 is equal to 1, and any off diagonal is equal to 0. So the identity matrix of 2 is equal to 1, 0, 0, 1. As you can see, the diagonal entries is equal to 1. I3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Which is equal to 1. The identity matrix comes in handy when we want to solve systems of equations using our matrix algebra. If we have matrix A times the identity matrix, it will simply become matrix A. If we have the identity matrix times A, we have A. A null matrix, all entries are equal to 0. So for example, 0, 0, 0, 0, 0, 0, 0, 0, 0. Anything times a null matrix, as with regular algebra, becomes 0. The transpose of a matrix is where we invert row to column and column to row. We indicate it by either a accent or a subscript T. For example, if we have matrix A equal to 1, 0, 3, 2, 1, 1, 0, 1, 1, a transpose would be equal to row 1, row 1, row 1 becomes column 1, so 1, 0, 3. Row 2 becomes column 2, so 2, 1, 1. And row 3 becomes column 3, 0, 1, 1. And we can close our matrix. The inverse of a matrix is indicated by A minus 1. The properties can be found on page 74, and you need to go through this, but the properties of the inverse becomes much clearer and its usefulness in chapter 5. One useful property is that if you multiply a matrix with its inverse, you will get the identity matrix. There are easier ways to solve a system of equations, which we'll do in chapter 5, but one way is if we have the system of equation AX equal to D, and we multiply both sides with A's inverse. we find that the identity matrix, because we have this property, gives us the identity matrix times X will be equal to the inverse of matrix A times the constant matrix. So X will be the inverse of matrix A times D. So if we have, for example, the system x1 plus x2 plus x3, I'm just going to do this in a different color for the example. So let's say example x1 plus x2 plus x3 is equal to 0. 12x1 plus 2x2 minus 3x3 is equal to 5. 3x1 plus 4x2 plus x3 equal to minus 5. And I give you the inverse of matrix A will be 14 over 35 minus 21 over 35, 42 over 35, 3 over 35, minus 2 over 35, and minus 1 over 35, minus 5 over 35, 15 over 35, and 10 over 35. If we want to solve this system of equation using the information that we have, we know that x is equal to the inverse of A1 times D. So you are given the inverse of A. We will cover in chapter 5, we cover how we get this inverse. Can you already note that all the denominators of the inverse are the same? Remember that for chapter 5. What is our D matrix equal to? It's equal to 0, 5, and minus 4. So now we have a simple matrix multiplication. So first, check conformability. So the inverse of A is a 3 by 3 matrix. And D is a 3 by 1 matrix. So yes, what will we end up with? We will end up with by 3 by 1 matrix. If you calculate this, this is equal to 1 minus 2 and 1. So x is equal to 1 minus 2 and 1, which means x1 is equal to 1, x2 is equal to minus 2, and x3 is equal to 1. If we replace these values into our equation, so 1 plus negative 2 plus 1 is equal to 0. So we know we've calculated this correctly. Section 4.7 is not important for this course.